Euclid begins the elements with 23 definitions, which are going to be the main subject of this video. But before we get into them, we have a few things we need to talk about. First, let's talk a little bit about geometry. So the basic idea of geometry is that it models objects in space. Here we have a cube, which is a three-dimensional object, or as the Greeks would have called it, a solid. We'll talk a little bit more about dimensions when we get to the definitions, but we should have some intuitive idea about what they are. One important thing to note is that geometric objects are really idealized versions of real objects. So for example, the sides of a geometric cube all have exactly the same length, whereas in reality something that is shaped like a cube probably is going to have small imperfections. In fact, the diagrams that we draw in geometry are also necessarily inaccurate to some extent, because we can't really draw something, for example, that has length but no width like a line does. A big question then is whether the objects of geometry really exist or if they're just ideas. If you're familiar, this should remind you of Plato's ideas about what he called forms, where he asserted the actual existence of abstract objects in some other plane of existence. We should also talk a little bit about the style of mathematics that we will be doing. One thing that may surprise you is that we won't be seeing any numbers in the elements. Our modern geometry is typically coordinate-based, where every point is identified by a unique set of coordinates, as you can see in the diagram here. But this idea is relatively modern. It was first developed in around the 1600s. The ancient Greeks had no method to identify the positions of geometric objects other than in relation to the positions of other objects. What the ancient Greeks were trying to do was to prove general results about geometric objects. If you aren't familiar with mathematical proofs, the idea is that we start with a collection of statements which we know to be true, then we follow some logical steps in order to demonstrate some further result. We will be starting out with relatively simple proofs, so things should start to make sense as we go if you haven't seen them before. Notably, in geometric proofs, we sometimes need to construct a specific object, and in this case, we also have to prove that the thing we constructed has the properties that we claim it does. A question that naturally arises is, how do we know what we can assume to be true for our proof? Naturally, once we prove a result, we can use it in later proofs, but we have to start somewhere before we can start proving things in the first place. The ancient Greeks thought a lot about this and decided that it was necessary to decide on a starting set of assumptions on which to build everything else. In modern mathematics, we call these axioms, and we'll talk about Euclid's axioms in the next video. So this is how Euclid laid out the elements. He chose a small set of starting assumptions, he provided some definitions, and then he proceeded to prove propositions. There are no assigned exercises or any kind of motivation given. The propositions just proceed one after another with no intermediate writing. The elements is fairly unique in this sense, and it is certainly very different from modern math books. But part of the beauty of the elements is that it still tells a very interesting story in this style. Speaking of exercises, any mathematician will tell you how important it is to do them. As the mathematician George Polya said, math is not a spectator sport. Therefore, I will be inserting extra problems at the end of the videos for you to try out on your own. I will choose problems that can be solved using the propositions and techniques that have been introduced so far. And I highly recommend trying these problems as you go. The ancient Greek proofs contained three main components, which were enunciation, proof, and conclusion. So the idea was that the enunciation would state what is given and what is sought, meaning what we're trying to do. The proof uses reason to produce what is sought, and then the conclusion states what we have done. The conclusion can feel a little bit redundant since it's kind of just restating the enunciation in some ways. So in modern translations, this is usually abbreviated. What you will probably see is the acronym QED. This stands for the Latin phrase quod erat demonstrandum, which means that which was to be demonstrated. For the propositions which show how to construct something, we will instead see QEF for quod erat faciendum, meaning that which had to be done. So there's kind of a subtle difference, but the main idea is that QED will be at the end of proofs and QEF will be at the end of constructions. There's a specific proof technique that shows up a lot in the Elements and requires a little bit of extra explanation. We call it reductio ad absurdum, which is Latin for reduction to absurdity. The underlying idea is that a statement must either be true or false, but it can't be both. So if we show that it is impossible for a statement to be false, we must conclude, therefore, that it is true. So the way that this will usually look is that we'll have a statement that we want to prove, we'll assume that that statement is actually false, and we'll use that assumption to reduce to an absurdity, meaning something that cannot possibly be true, a contradiction. And then we'll conclude, therefore, that the original statement must have actually been true. Now, this technique might feel a little bit strange at first, but once you get used to it, it really is an invaluable tool which greatly simplifies a lot of proofs. It's worth noting that the idea that a statement is either true or false, but not both, is a logical premise called the law of excluded middle. This rule is generally accepted in modern mathematics, but there have been some criticisms of it. And it is a little bit unsatisfying, perhaps, because it can lead to proofs that don't actually provide a direct proof of what they're claiming. But nevertheless, it is used extensively both in the Elements and in modern mathematics, so we are going to follow suit. So now we come to the definitions. The first few are going to sound a little bit strange at first. This is mainly because points and lines are difficult to define without going in circles, even though we have some intuitive idea of what they are. In fact, in modern geometry, we often just leave points and lines as undefined objects which have certain properties in relation to one another. So let's get started. Definition 1, a point is that which has no part. Definition 2, a line is breadthless length. Definition 3, the extremities of a line are points. And definition 4, a straight line is a line which lies evenly with the points on itself. Before we talk about what these definitions mean, let's take a look at how to use the GeoGebra software. So if you download the desktop version of GeoGebra, this is what it should look like when you launch it. It has a lot of features. Most of them we aren't really going to be using. We're going to click on geometry over here. You'll notice that that will hide the axes and the grid. You can get those back if you want by right-clicking. Now on the top here there are a lot of different tools. Each one of these has a little drop-down. Most of these tools are for more advanced geometric constructions, so we won't be using a lot of them. And in particular, we'll be starting out with only a few tools. So we talked about how the only tools we have in geometry are the compass and straight edge. So the only things we'll be allowed to do at the start are create points. We can draw lines, so we can draw a line connecting these 2 points. Drawing lines is done using the straight edge. And then the other thing we can do is the circle with center through point. This is done using our compass, so we can make circles if we want. Now, as we go through the elements, we'll be proving that we can construct other things. So, for example, at some point we'll prove that we can construct a line that is parallel to another line. And once we prove that, we can use these more advanced tools instead of having to go through the basic construction every single time. So you can think of it as we're going to be unlocking all of these tools as we go. So let's talk about the first four definitions. Euclid says that a point is that which has no part. So what exactly does this mean? Now, we generally think of a point as a single location in space, and in fact, there isn't really a distinction between that single location in space and the point that lives there. The other property that points have is that they are indivisible. So, for example, we can break a line segment down into smaller line segments, but we can't break a point down into smaller points. And in fact, in geometry, there isn't really anything smaller than a point. So Euclid's definition that a point has no part might sound a little bit like he's saying that points don't actually exist. But this is not the case. So what Euclid probably means by this is that points are indivisible. They're the units of geometry. The reason that Euclid describes a point in the negative, saying what it doesn't have, is probably because the Greeks thought of it as taking away dimensions one at a time. So if you start with a solid, you have 3 dimensions. Then you move down to a plane, which only has 2 dimensions. The next is a line that has 1 dimension. And once all 3 of the dimensions have been taken away, what you're left with is a single point with no dimensions. Or, as Euclid says, no part. So the next definition says that a line is breadthless length. So this is really just saying that a line is a one-dimensional object. We can go left and right on this line, but we can't go up and down. The third definition tells us that the extremities of a line are points. So in this case, we see that the endpoints of this line are the 2 points A and B. Additionally, if we were to divide a line into 2 separate segments, that point of division would also be a point. So a couple more notes about lines. The line I've drawn here is what we would now call a line segment, meaning it's finite in length. We can also have an infinitely long line, of course. In the elements, there's no word to distinguish between finite lines and infinitely long lines, so we'll have to kind of determine that through context. Another thing we do in modern mathematics is we think of the length of a line segment as a number. Now, the word number to the ancient Greeks typically only referred to whole numbers, 2, 3, 4, etc. So to the ancient Greeks, the length of a line segment was something entirely different than a number. They called the length of a line segment a magnitude. Now, moving on to Euclid's fourth definition, there's a distinction between straight lines, like we see here, and curved lines, like a circle, for example. But a straight line is, again, something that's kind of difficult to define, and Euclid's definition about lying evenly with the points on itself doesn't really say very much. There are a few other ways that the ancient Greeks defined straight lines. Proclus, for example, defined it as a line stretched to the utmost. So you can imagine taking a piece of string and stretching it as far as it can go, and that will give you a straight line. Another way of thinking about it is that it is the shortest distance between 2 points, although that presupposes that we have some way of knowing what the distance between 2 points is. What we really want from straight lines is that we want 2 points to uniquely determine a straight line. So what that means is that if we take any 2 distinct points, like h and I here, we want it to be that there is one and only one straight line which passes through those 2 points. Now, throughout the elements, we will pretty much exclusively be working with straight lines and circles. There are, of course, other types of curved lines, but the study of those is left to higher geometry. Note that we will often refer to straight lines simply as lines. It should typically be clear what we're talking about, though. Another thing which Euclid doesn't mention but assumes is that if two straight lines intersect, they intersect at a single point. And I'll show here the intersect tool, which allows us to select two different objects, and it will give us the point of intersection. Another interesting thing to note is that while we mentioned that the extremities of a straight line are points, there are lines that don't have extremities. So for example, an infinitely long line doesn't have endpoints because it never ends. And similarly, a circle doesn't have endpoints because it loops back into itself. One more thing to mention about lines is that in modern geometry, we often think about lines as being made up of points. However, the ancient Greeks had a little bit of conceptual difficulty with this idea. So because points are indivisible and a line is divisible, they had trouble thinking about something divisible being made up by an accumulation of indivisible objects. Instead, they thought of a line as being made by the continuous motion of a point, or as Proclus said, the flux of a point. So what this means is that if you imagine taking a point and moving it through space, the path that that point traces out will be a line, not necessarily a straight line. So next we have some definitions about surfaces. Definition 5, a surface is that which has length and breadth only. Definition 6, the extremities of a surface are lines. And definition 7, a plane surface is a surface which lies evenly with the straight lines on itself. So these definitions are pretty similar to the definitions for lines, just now we're talking about a two-dimensional object. So we won't really say too much about these ones. A surface you can think of as the skin of a solid, or the outside, the part that you can see from outside of the solid. And then a plane surface is similar to a straight line. Planes can get pretty complicated, so we're not going to say too much about them here. A couple of things to note though. A plane is uniquely determined by three non-collinear points, meaning that if you have 3 points that aren't on a single straight line, there is one and only one plane which passes through those 3 points, so kind of similar to a straight line being uniquely determined by 2 distinct points. Another property that planes have is that if a straight line passes through 2 distinct points on a plane, then all of the points of that line are on that plane. Now, for most of the elements, we are going to be working in a plane, which we call the Euclidean plane. This is because three-dimensional geometry is a lot more complicated, so that is reserved for the last couple of books of the elements. Before we move on, let's talk really quickly about how the ancient Greeks viewed dimensions. So we mentioned that a point has 0 dimensions, a line has 1 dimension, a surface has 2 dimensions, and a solid has 3 dimensions. So according to Aristotle, the dimensions were 1, up and down, which is represented by length, 2, before and behind, represented by depth, and 3, left and right, represented by breadth. So you can imagine yourself standing in 3-dimensional space, and each of those 3 directions is one of the dimensions. As an example, length was said to be what is meant when one asks for the length of a road or a wall. The actual object in question may have some breadth, but we are only interested in the length property. So now we have angles. Definition 8, a plane angle is the inclination to one another of 2 lines in a plane which meet one another and do not lie in a straight line. Definition 9, and when the lines containing the angle are straight, the angle is called rectilineal. So we typically think of an angle as something that looks like this, where you have 2 straight lines meeting at a point and then stopping. The ancient Greeks, though, also liked to work with what they called curvilineal angles, which you get, for example, when two circles meet at a point, or when a line and a circle meet, maybe like that. This probably seems a little bit weird, and we won't be seeing too much of it in the elements, but it is going to start to show up later on. Now, in Euclid's definition, he says that the lines must not lie in a straight line with one another. This probably just means that the lines must not be continuous with one another, meaning if they were the same line, then we wouldn't have an angle between them. So the important thing about angles is that they're not really measuring a distance, since the lines that make up the angle keep getting further apart the further you go. Really what they're measuring is the rate of divergence of the lines. So, for example, if we were to do another angle here, let's make this one a lot wider. These two lines diverge on the right a lot more quickly than the two lines on the left. Now, there is a specific kind of angle which is going to be especially important, which is the right angle. So we have definition 10. When a straight line set up on a straight line makes the adjacent angles equal to one another, each of the equal angles is right, and the straight line standing on the other is called a perpendicular to that on which it stands. Then, definition 11, an obtuse angle is an angle greater than a right angle, and definition 12, an acute angle is an angle less than a right angle. So let's visualize what this looks like. Suppose we have a straight line AB, and then let's put another point in the middle there, C. And then let's say that we have a line segment coming out of C to the point D. And what I'm going to do here is I'm going to use the angle tool to give us a measurement of these two angles. You'll see they have little round symbols there. Now, as I move this straight line around, so this is the straight line standing on the other straight line, as Euclid says, you can see that the angle on one side gets smaller and the angle on the other side gets bigger depending on which way I move it. So there's a point somewhere in the middle here, and I might be able to, there we go, where those two angles are exactly the same. And you'll see that when I get there, it changes the little symbol so that it's a square instead of a curve. So that's what we mean when we say a right angle. We mean the angle where the two angles on either side are the same. Then Euclid also says that the two lines that are making the right angles are said to be perpendicular to one another. And he additionally says that if we have an angle smaller than a right angle, we call it acute, and an angle bigger than a right angle is called obtuse. Now, one thing we should mention at this point is that when Euclid defines an object, he is not actually making the claim that the object exists. For all of these objects, we are going to have to prove that they exist before we can use them. There are only two exceptions to this, which are points and lines, which we have to assume exist or we don't really have anything to work with. So moving on, definition 13, a boundary is that which is an extremity of anything. Definition 14, a figure is that which is contained by any boundary or boundaries. Definition 15, a circle is a plane figure contained by one line such that all the straight lines falling upon it from one point among those lying within the figure are equal to one another. And definition 16, that point is called the center of the circle. We've already talked, of course, about boundaries. For example, the boundaries of a straight line segment are points. An example of a figure is something bounded by straight line segments, which we would call a polygon, for example, the triangle here, or as Euclid defines next, a circle. Now, an interesting question is, when we talk about a figure, are we talking about the boundary, the part inside the boundary, or both? So Euclid's definition makes it sound like just the inside part is the figure. However, sometimes in the elements we'll talk about circles as if they are the straight line that bounds the circle and not the part on the inside. And then other times we'll talk about figures as if they are the boundary plus the inside. So it's not really clear which one we mean, and it'll be kind of different in different situations. Now, a couple of notes about circles. Euclid is going to assume that we know that the word circumference means the line that is bounding the circle. And as we mentioned previously, circles are going to be the only curved lines that we'll be really seeing in the elements. Now, Euclid's definition about straight lines falling on the circle means that if we take a line segment connecting the center to the circumference, that line segment is going to have the same length no matter which point on the circumference we pick. Next up, definition 17. A diameter of the circle is any straight line drawn through the center and terminated in both directions by the circumference of the circle, and such a straight line also bisects the circle. And then definition 18, a semicircle is the figure contained by the diameter and the circumference cut off by it. And the center of the semicircle is the same as that of the circle. So let's visualize that real quick. We'll take a point on the circumference of this circle and we'll draw a straight line connecting the center to that point. And then we'll mark over here the point on the circumference opposite. And then I'm going to hide this line and make it just a line segment connecting those 2 points. So this is a diameter. It's a straight line passing through the center of the circle and then terminated on both sides by the circumference. We can move it around. So the word diameter means measurement across. The prefix dia means across something. This word was also used at some point by the ancient Greeks for squares and parallelograms, but later they started calling these diagonals. So the diagonal of a square connects the 2 opposite corners. Now, Euclid tells us that the diameter of a circle divides the circle into 2 equal areas. This should feel pretty obvious looking at it. He also tells us that a semicircle is a figure bounded by half of the circumference of the circle and the diameter. So a diameter of a circle will split it into 2 semicircles. Next we have definition 19. Rectilineal figures are those which are contained by straight lines. Trilateral figures being those contained by 3. Quadrilateral, those contained by 4. And multilateral, those contained by more than 4 straight lines. Definition 20. Of trilateral figures, an equilateral triangle is that which has its 3 sides equal. An isosceles triangle, that which has 2 of its sides alone equal. And a scalene triangle, that which has its 3 sides unequal. And then definition 21. Further, of trilateral figures, a right-angled triangle is that which has a right angle, an obtuse-angled triangle that which has an obtuse angle, and an acute-angled triangle that which has its 3 angles acute. So we're classifying the triangles here. What we can see is we can classify them by the lengths of their sides or by their angles. And in all, there are 7 different possible triangles. For example, the right-angled isosceles triangle is one of those. When Euclid speaks of rectilineal figures, he is of course talking about what we call polygons. So a triangle is a polygon with 3 sides. A quadrilateral is a polygon with 4 sides, etc. Next we have definition 22. Of quadrilateral figures, a square is that which is both equilateral and right-angled. An oblong, that which is right-angled but not equilateral. A rhombus, that which is equilateral but not right-angled. And a rhomboid, that which has its opposite sides and angles equal to one another but is neither equilateral nor right-angled. And let quadrilaterals other than these be called trapezia. And finally, definition 23. Parallel straight lines are straight lines which, being in the same plane and being produced indefinitely in both directions, do not meet one another in either direction. So here we have a classification of quadrilaterals. When we say equilateral, we mean that all of the sides are equal to one another in length. When we say right-angled, that means that all of the internal angles of the quadrilateral are right angles. Now, some of these definitions are not actually going to show up in the elements. For example, he never mentions an oblong at any other point. Probably he was just trying to be comprehensive here in the definitions, since this is supposed to be a guide to elementary geometry. Interestingly, though, he doesn't define a parallelogram, which is a quadrilateral whose opposite sides are parallel to one another, which is a little bit strange since parallelograms do show up in the elements. Now, I'm not going to show what the different types of quadrilateral look like here. You can try that on your own if you'd like. But we do need to talk about parallel lines. So Euclid's definition of parallel lines, the key point is that they never intersect one another. So no matter how far you zoomed out on these two parallel lines, they're never going to meet in either direction. An alternative way of thinking about parallel lines is that they are lines which never converge, meaning get closer together, nor diverge, meaning get further apart. So the distance between them, at least in Euclidean geometry, is always going to be the same. Note, of course, that if we were not talking specifically about straight lines, it would be possible to find lines that converge forever without ever actually intersecting. An example of that is the parabola and its asymptote, which always get closer together but never actually meet. So that is the final definition from the elements, so we'll stop this video here. In the next video, we're going to look at the axioms that Euclid chose for his system of geometry.